Hi, good afternoon. So last class we were discussing fuzzy logic and fuzzy clustering. It's like I was saying that just as relational logic, the variables are binary variables, true or false, or one or zero. In fuzzy logic, the variable is a continuous variable which can take any value between zero and one. These are and here and in fuzzy set theory, the given element will be a member of a set with a certain membership function. So you can say that an element is a member of a set with some membership, some value between 0 and 1. So therefore, an element can be present in multiple sets with different levels of membership. Now, that kind of a notion is quite useful for fuzzy clustering because when you in clustering or let's say k-means, you allocate data points to clusters, and clusters are like sets, and data points are like elements. So generally in k-means clustering, you only have a given point can only be in one cluster. It cannot be in multiple clusters. Whereas in fuzzy clustering, a given point, suppose it's close to the border between two centers, clusters, it can be allocated to both clusters, but with different levels of weightage, right? So that is where the idea of membership function comes into picture. Now, how do you define formally this notion of a membership function? So to answer that question, we started with k-means clustering, which is something that we are familiar with, and slowly we are trying to migrate to fuzzy clustering. So in k-means clustering, a given data point is allocated to only one cluster uniquely, whereas in fuzzy clustering, a given data point can be allocated to all clusters, but with different levels of membership, Wij. Okay, so this membership in k-means can be written like this. Wij will be a matrix, right? Where the on the rows we have J, which represents the data points. So in this case, there are 7 data points. And columns are clusters. In this case, there are only 2 clusters. So a given data point can only belong to one cluster. So therefore, in a given row there can be only one, and all the other entries must be 0. So sum of all the entries in a row must be equal to 1. So that is first condition on this membership matrix. Then second thing is the sum of all entries in a column. Right? Traditionally, it indicates the number of points in the corresponding cluster because each column corresponds to one cluster. So the same thing now in case of fuzzy clustering, it is sigma wij j equal to 1 to n, right, for a given I. It represents some kind of a mass, right, of the ith cluster. So now we said let us write down the sum square distance because which is a key idea in k-means clustering. And in fact, you can derive k-means clustering from this notion of sum square clustering. So we said we'll start with the simple, right? So this is how you would write the sum square distance in k-means clustering. So let me change the color a little bit. Comparing, so this, let's say I have an mi here and another mi here. So this is, I'll call this m1 and I'll call this m2. In this loop, if I have all possible combinations of xi and mi, xj and mi, then I'll take the distances from not only these points to this m1, but also from this points to this m1, which is not right because you have to calculate distances only to the nearest neighbor. So if I have completely a double loop, you'll be looking at all possible combinations of data points and mean vectors or centroids. Whereas if I want to use this double loop, but actually get this expression, the first expression, right? So that is equation for equation 2 to look like equation 1. I will use this membership matrix Wij. Then even in this form, this expression and equation 1 expression, equation 2 expression are the same. Because Wij is 0 for all these cases where the combination is invalid, right? I cannot compare data point 4, right, to cluster number 1. So all those entries are 0. So this is okay. So now here what we will do is, this is starting point to write down the membership matrix and a new SSC for clustering. So here what we will do is, so here Wij, traditionally in k-means it is Wij, so in k-means, right, Wij, if you take it in Wij is either 0 or 1. Same thing in fuzzy, right, Wij is in the set 0 and 1. Okay, so it can vary continuously within that interval. This is what. But in addition, we'll use one more thing. We'll use a quantity called P. Okay, P is a power and exponent, and P varies from 1 to infinity. So P will denote the kind of level of fuzziness. Okay, so if P is equal to infinity, right, it will be like k-means clustering. If P is 1, it will be extremely fuzzy. Okay, so let us see how. So actually, no, it's other way around. P is infinity is like totally fuzzy, right? That is, every point will belong to every cluster, and there's no distinction at all. Then that's not actually clustering. When P equal to 1, a given point is given to only the nearest cluster or nearest centroid, and that is like exactly like k-means clustering. So for P, any value between 1 and infinity, it is something in between. A given point can belong to not only the nearest cluster, but also to other clusters to lesser extent, starts getting fuzzy. So let us see how this P works. So for that, first we have to see, right, how do you even calculate this membership matrix Wij? What is Wij and how do you calculate it? So given the data set and given the data set, how do you calculate the membership matrix and the mean vectors or centroids? So in traditional k-means, again, let us take inspiration from k-means. In traditional k-means, you first calculate the centroids. So you first do allocation and then calculate centroids by taking average. So here, so in k-means, so mi is equal to mean of all points in cluster I. Okay, now same thing we'll do here slightly differently. In fuzzy, mi is given as sigma wij times xj. X is j data point. So j goes from 1 to n. Okay, so j equal to 1 to n. So you see what is happening here. If you imagine, so I'll have power p. Let us take the simple case, so where you want to constantly compare with the traditional k-means, right? So let us say p equal to 1. Then you will just have wij times xj. Then let us say wij's are exactly like this binary values, like in case of k-means. So then what will happen is, I'm using all wij's for a given I because I want to know the centroid of the ith cluster, right? So wij's will be non-zero only for that cluster. For all the data points that are belong to that cluster, wij's will be non-zero. Okay, for all the others, wij's will be 0. So it will be 1 for all the relevant points and 0 for all the irrelevant points. So in this summation, I will be only adding up all the points that belong to ith cluster, or all the points for which the ith centroid is the closest, if I look at it in terms of k-means clustering. Then the denominator, sum of wij p, let's say p equal to 1, and sum of wij, like we said here, is equal to number of points. So if you look at this, basically what we are doing, if you look at it purely in k-means terms, that means you take wij's equal are all binary entries, and p is 1, right? So for p equal to 1 and wij equal to 0 or 1, then this is just like in k-means, because you are just calculating the mean value. Okay, so this is how you calculate so given the data points and given some, initially you take a random weight matrix, WAJ, and you have the data points. Then you use this expression to calculate the MIs. Now, given the MIs, you have to calculate the WAJs. So how do you calculate WAJs? So here, given MIs, calculate WAJs. So in k-means, it is done by okay, so it is done based on nearest neighbor, right, criterion. Okay, so for a given j, data point j, if a given ith centroid is closest, right, then that the Wij will be equal to 1, otherwise it is 0. So this is how you calculate Wijs if it is in k-means terms. Now we'll do the same thing sort of fuzzy sense. Okay, so how does it work? So in fuzzy clustering, this Wij has a so can anybody intuitively tell me what will be a good expression to use for Wij? So basically it has to indicate that a given point belongs to a cluster represented by a given centroid, Mi, right? To what extent a given point, so Wij represents to what extent a given data point Xj belongs to Mi, so a given Mi. So this notion, how will you mathematically capture this? Any idea? In traditional k-means, it is based on nearest neighbor, right? But if you want to allow some fuzziness, what is a good way to capture this idea? Any intuitive suggestions? Hello, Kishanji, are you there today? Okay, so basically, you see, thing is, if a intuitive idea is, if a given data point xj is very close to Mi, then the corresponding weightage should be high. The corresponding membership function should be high. If it is far from it, it should be low. That means if it is actually very close, it's actually identical to Mi, it should be 1, right? And it should, and because it totally belongs to that cluster. And if it is very far from it, to the extent it should go down to 0 as distance increases. So how do you capture that notion, that intuitive notion in a mathematical formula? So what they have done in fuzzy clustering is they have taken a slightly complicated expression, but which basically gives you the same intuitive concept, which is distance xj mi, a distance square to the power of 1 by p minus 1 divided by sigma q goes from 1 to k. Again, one more such expression, 1 by distance square xj mq. Okay, and the whole thing power 1 by p minus 1. See, one way to do this is, one way to come up with a function like this, where if xj and mi are very close, the quantity should be high or close to 1. Very far, it is close to 0. One simple way to get it is use the Gaussian function. That Gaussian of the distance between xj and mi will have exactly those properties. but they haven't used it in fuzzy clustering literature. They've used something slightly different because that quantity should be increasing with decreasing distance. So you cannot use distance itself. You should use some kind of inverse of distance. The Gaussian has that property, but they haven't used it. So they use inverse of distance. So 1 by distance square and all that. But problem is if you just use inverse of distance, then if xj and mi are the same, so xj goes and sits on mi, distance becomes 0 and this quantity will blow up, and obviously you don't want that. So to normalize that, right, they divide this quantity. So you take the point xj and take all the mi's. So this is m1, mi, etc., etc. Take all these distances. Take the inverse of them. So if I'm comparing with mi, take the inverse of this distance, and in the denominator you have the inverse of all the other distances. Okay, so that if this is really low, the distance to mi, particular mi is really low, then this quantity will be to the extent high. Okay, and even if xj actually becomes identical to certain mi, that distance will be 0, so 1 over that will be infinity. But you can show that if you divide numerator denominator by this, that distance and then let xj tend to mi, then the whole thing will simply go to 1. It won't blow up. Okay, so that is what is nice about this expression. Now, one more thing that they use here is this p factor, this p power in the power. So p is the power in this wij power p. But same thing here, you don't say p, but you do 1 by p minus 1. So there is a reason behind this. I'll come to that in a minute. So given some data and given some random initial w's, you do two things, right? Sorry. Okay, so in fuzzy clustering, first step, you take that random initial w's, calculate the mi's, and take those mi's and then calculate w's, and this you do back and forth. So from here to here and here to here until convergence. Okay, so that is how it works. So now we need to also see something interesting. What happens when p is varied? So when p is infinity, we said it is totally fuzzy, and when p is 1, it is like k-means, and how exactly does it happen? Let us look at that. So p tends to infinity case, right? So what happens? So let us look at this expression. 1 by distance square xj mi. Okay, this whole thing to the power of 1 by p minus 1, right? And denominator you have again sigma q equal to 1 to k, and 1 by distance square xj net to all other uh, centroids. You take power p minus 1. Okay, so now when p tends to infinity, so I'll define h is equal to 1 by p minus 1. So therefore, as p tends to infinity, h tends to 0. So this is wij, right? Now as h tends to 0, okay, wij will be equal to, so this whole thing to the power of 0, which is 1, assuming that distance is uh, finite and non-zero, right? And divided by, again, so everything will be, assuming all the distances are non-zero, so all the entries in the denominator also will tend towards 1. So it will be 1 plus 1 plus, right, k times plus 1. So is equal to 1 over k. What is it saying? So earlier in K-means case, right, only the centroids that are closest to a given point have weightages of 1 and all others are zeros. Whereas here, all the centroids have equal weightage. So instead of 1000, you have half and half. That means the data point belongs to both classes with equal weightage. Okay, so that is what it means. So uh, a given x data point xj belongs to all clusters with equal weightage equal to 1/k. So that is like, you know, that is totally fuzzy, right? Whereas if you look at the other extreme, because we said p can only vary between okay, so 1 and infinity. Did I say? Sorry, it should not be equal to. Okay, so it's 1 and infinity. So that when it goes to 1 or p tends to 1, what happens? Right. So again, let's take this thing h equal to 1 over p minus 1. Okay, so when p tends to 1, h tends to infinity. So when h tends to infinity, so look at the same expression. So now we want to show that your WHs now will start looking like your binary WHs that you got in case of k-means clustering. So it will just look like this 100 kind of thing. How do you get that? So for that, let us look at, let us take, like, consider some data point, consider xj, and let mi star is the nearest neighbor, okay, of xj. Right, so this is the nearest neighbor, just in case you forgot. Then your expression will be something like this. Your wij will be equal to, so what we'll do now, multiply, so multiply numerator and denominator by distance square xj, uh, xj mi star. Okay, so that whole thing to the power of h. Okay, so that's h. So what happens if you do that? Oops. Okay, so I'll just take, if you take that, the numerator you will have distance square xj mi star by distance square xj mi, because the normal expression is this. So in this expression, I'm just multiplying numerator denominator by this, because for a given data point xj, there is a certain nearest neighbor centroid, which happens to be, let us say, mi star. So I'm taking that expression, multiplying numerator denominator by the distance square. So now let us see what happens. So this whole thing power h, because I've used power h here also, divided by sum over q equal to 1 k dist square xj mi star by dist square xj mq. Okay, this whole thing power h. Now h is tending to infinity here. Now you see that mi star happens to be the nearest neighbor, which means that this quantity, right, will be the, so for now we have only two cases. Okay, so for a given j, so for a given, okay, for a given j, you have, there are two cases. I is equal to I star. So the I that you're considering happens to be the nearest neighbor, or I is not equal to I star. In only two cases, right? Now what happens to the weightage if I is equal to I star, I is not equal to I star? So if I is equal to I star, denominator, both these terms will be the same. It is, so this is actually 1 power h, right, is 1, h tends to 1 also, it is 1. Similarly, denominator and the numerator. In the denominator also, you will have one of these terms equal to 1. All other terms will be less than 1 because the distance j mi star, this is the nearest neighbor distance. So that is less than all other distances, right? So all other fractions in the denominator will be less than 1. And only one of the terms will be equal to 1. So then what will happen is, wi for I equal to ij, wij will be of the form 1 by 0 plus 0 plus 0 0 plus 1. There will be only 1 in the denominator, which is equal to 1. Okay, so that is what will happen for I star. So I can actually, okay, so where I equal to I star. Or if I is not equal to I star, in the denominator then, the d square xj mi star is less than d square xj mi, because mi is not equal to mi star. So this quantity will be less than 1. In the denominator actually, all the quantities except 1 will be less than 1. Only one quantity will be equal to 1, because for that mq will be equal to mi star. Because you are going through all q, one of them will be equal to mi star. So in this case, what happens is, oh, sorry. So for I equal to I not equal to I star, wij will be equal to, so, and for h tends to infinity, of course, here also h tends to infinity, it will be 0 by 0 plus 0 plus 0 plus and etc. up to 1. So, okay, so that is equal to 0. So for p tending to 1, the wij's you get will be identical to the wij's you will have for k means. Okay, so for you can't say p equal to 1, because when p equals to 1, something blows up. So I'll just say p equal to 1, right? Fuzzy clustering is equal to k means. For p tending to infinity, fuzzy clustering is totally fuzzy. Okay, so that is how it works. So if you have data where you want the points to be allocated to multiple clusters with relative weightages and so on, right? This is a good thing. But what I feel is it is more of historic value, because of the modern techniques of clustering in higher dimensions and all that. Fuzzy clustering has a nice, beautiful theory, very interesting and all. But in the current day, I'm not seeing many practical applications, happening these days. But it's interesting to know, because it has very elegant theory, and it was a big hit, at some time. In the 70s and 80s, it was a big hit. Okay, so let us wind up this topic. If you have any questions, I'll be happy to answer.
Sir, how can we define P here?
So you choose P, just like in K means you choose K. Here you have to choose P.
So is it like, how many points that particular no how many clusters that a particular I belongs to? Is it what P is?
No. So now for a given data point xj, the idea of how many clusters it belongs to doesn't have any meaning. It's because everything is fuzzy, everything is gray. There's no black and white. A data point belongs to a certain cluster with more weightage or less weightage. There's nothing like does it belong at all to this cluster, right? Because you think of your wij matrix. In K means it is binary. That means a given data point either belongs to a cluster or doesn't belong to a cluster. There's nothing in between. Now that binary matrix, now you make it all continuous variables, fill it with continuous variables. right? So that means a given point can belong with a high extent to one cluster, but to a lesser extent to other clusters, and so on and so forth, right? It is so everything is fuzzy. It's not a categorical allocation of data points to clusters. In some philosophy, it's totally different, right? And to what extent data points are allocated to clusters is indicated by the W matrix. And the algorithm tells you how to iterate. So just as in k-means, you have iteration, right? You go from, so you first allocate the points to the centroids based on Ayres-Neighbor criterion. Then you take average of all the points in a given cluster and recalculate the centroid. And again, reallocate, recompute centroids. These steps go on and on in k-means. Same thing is happening in fuzzy clustering also. Only thing is, when you say allocation in fuzzy clustering, it means calculating the W matrix. So in this process, you have to choose a P. Oh, incidentally, the typical choice of P is equal to 1. Because, equal to 2. Because when P equal to 2, 1 by P minus 1 becomes 1. So you can get rid of the exponent, that power completely. Okay, so I hope I answered the question.
Sir, I got it. So my doubt is like, if we say K, then we refer to number of clusters here. So in K means, what does P refers to?
Here also K is number of clusters. Only thing is, when it comes to allocating points to clusters, it is not binary, it's not black and white. A given data point can be given to many clusters, but at variable weightages. And in the extreme case, when P goes to infinity, it's a trivial clustering. It's actually no clustering. Every point is put in every cluster, which is useless. It's not saying anything. But that's what happens when P goes to infinity.
Okay, sir.
Okay, thank you. So let me start just the basic idea of a next topic, but I'll actually, get into the details of it in the next class. So, can you see the slides?
Yes, sir.
Density-based approach to clustering, right? Yeah. So this the fuzzy clustering nicely motivates this next topic, which is density-based approach to clustering. Because if you think of what we just did in fuzzy clustering, you have some data. Okay, let's have some data here and some data here, and a given data point, right, belongs to this cluster to a greater extent, and but belongs to this cluster to a lesser extent. So that's the kind of thing we have done, right? So same thing we can. So we have defined a function, right? That membership function, which is calculated by the 1 by distance square and all that. Now, same thing we can do slightly differently using what is called a density-based approach to clustering. Imagine I define a function. Okay, here, a function which represents the density. Why is it like this? Because I have a lot of points in this part of the space. So I have a function which is going high. And when I go away from this part, the points are becoming thinner. So my function is going down. Again, when I come to this part of the space, my function is picking up. Again, it goes down. Okay, so I'm just drawing a 1D picture just to keep the idea simple. So this is also density. So if I have a point, and so one intuitive idea here is density-based clustering is clusters are high density region. Right? Intuitively, are you okay with that idea? Because wherever you have cluster, the local density is high. What is density? So density is a mass per unit volume, but in this case, density means here there is no mass, number of points per unit volume. That is density. Okay, it is not easy to calculate. It can be computationally quite expensive, especially if your space is high dimensional and if your data is sparse. Your estimates can be totally off. But intuitively, that is what that is the idea of density, right? So when you have data like this, if I can calculate some kind of a density of this data, right? Then if I want to know if a given point belongs to this cluster or this cluster, I just plug into this density function. Okay, so this density function is like this. And I have some points here. There's high density of lots of points in this part. I'm considering a point here. I'll call this xj. Now I'm asking, is that xj, does it belong to this cluster? So now if I can construct some kind of density function for this data set, right, I just calculate, so I'll call this density function P1 of x, corresponding to this little cluster of data. So now if I just calculate this function, sorry, P1 of xj, so P1 of xj, right? Now this function, if you evaluate this function at xj, it's a small number. So if it's small, so you can confidently say that xj doesn't belong to this cluster to a great extent. It's kind of like, it's somewhere in on the outlying areas. But if I take another xj, we'll call this x p, right, and which is here, and if I evaluate, okay, so xj doesn't uh, belong to p1. Whereas if I take a point like this, if I evaluate p1, right, so so this is a small number. But if I take xp, and p1 at xp is a large number, so therefore xp belongs to p1. Okay, so in a sense, that's what we have done. So what we have done earlier is we looked at the distance of a given point to a given centroid. If the distance is small, right? So if you look at your wij, the matrix elements, right? If you look at the distance, if you kind of represent it as a continuous function of distance, if you vary xj continuously and calculate the wij as a continuous variable, it looks something like this. Because if the data point is bang in the middle of the cluster, you will have high value. If it is far from it, you will have low value. It looks like some kind of a hill, right? So if you can explicitly calculate that hill, now plug in this data point into that hill function, let's say p1 of x, right? And then if that evaluation is small, then I say data point doesn't belong to the hill. Evaluation big, it doesn't belongs to the hill. So like that, I can have multiple hills, etc. Each hill represents one cluster. So I can take a point and see, evaluate it. This is P1 of X, P2 of X, P3 of X. Okay, evaluate it for each function. If it is high, then it belongs to the cluster. So I'm just building up the intuitive ideas. The more formally it is slightly different. I'm just trying to. So there is a method called expectation maximization by Gaussian mixture models, and don't worry about the expression. The intuitive idea is very simple. We'll come to that later. So that hill I was talking about, that hill is, the function that they actually use is Gaussians. So you might have noticed that we keep on bumping into Gaussian functions, right? Because Gaussians have very nice mathematical properties in data analysis. So you'll keep on bumping into Gaussian. So please get used to Gaussians. Okay. So thing is, if you look at lots of real world data and real world distributions, right? And typically you will see that if you take, let's say, you manufacture some pipes, and the pipe diameter should be exactly equal to 10 millimeters. But if you actually manufacture it, there will be small errors. It can be 10.1, it can be 9.9, it's 9.99, and so on and so forth. So if you actually look at lots of values, all those numbers might vary around some mean value, which is your requirement of 10 millimeters. But it will actually vary around some mean. So this is your 10 millimeters, it will vary. And how much it varies, it is a standard deviation, all this stuff. And what is interesting is this curve is very often can be very nicely approximated by a Gaussian. Okay, so that is just a property. A lot of real world distributions have this property. Now, so let's say if you take these numbers as diameters of pipes, and you draw a histogram, and you know how to draw a histogram, right? You just bin it up and count the number of samples present in each bin. You'll typically find that around some mean value, you'll find a lot of entries in those bins. As you go away from the mean value, you'll find fewer and fewer entries, fewer and fewer samples. So that kind of histogram can be very nicely approximated using a Gaussian. And sometimes your data set can have multiple peaks. Then you say the data is multi-model. So this is where we come to the concept of clustering. Because in a given data set, I can have many bunches, many clouds of points. Okay, so each of them is a peak, right? So, so you draw a histogram and try to get at the underlying distribution, right? Wherever there is a peak in the histogram, you try to shove a Gaussian there. Now, each of these Gaussians will end up being a cluster. So this is the main idea. So the problem now is, given a data set, how do you fit it using a bunch of Gaussians? So this is the basic idea. So look at this. I'll show some examples in this class, and we'll actually get into the math from next class. So imagine, like, I have some data set which is given by the green points, and I want to fit because I can see that there are two clusters in this. I want to fit it using two Gaussians, and initially the Gaussians are like this. So Gaussian, normally what you might have studied Gaussian in one dimension, because it has a single mean and sorry, so single mean and standard deviation. So this is the mean value x bar, and so this is in one dimension. But if you look at it in two dimensions, so kind of, pardon my artwork, is, but it looks something like this. Okay, so right, so it will look like this, and it will have. So if you take a section of this somewhere, if you cut it, chop it somewhere, the Gaussian will have, if it is symmetric, the section will look like a circle. Otherwise, it doesn't have to look like a circle. It will, in general, look like an ellipse. Okay, because the variation, it could be high in one axis and low in another axis. In fact, more generally, it won't even look like this. It can even look like an rotated ellipse. Okay, so we'll come to all that later. So in general, we can try to fit Gaussians in n dimensions to data. So in this illustration, you have just two clusters, two clouds of points, and you start with two Gaussian, the blue one and the red one, and each of them are symmetric initially. So, because we don't know anything about the data, so make it simple, keep it simple to start with. So then there's an algorithm which keeps on updating the parameters of the Gaussian, okay, and keep on moving them around. So updating means you move the midpoint of the Gaussian, and you can easily see intuitively that the center of the Gaussian is very similar to your centroid that you have been using in k-means clustering, in k-medioids, in right fuzzy logic. I mean, the same notion again shows up differently in different algorithms. So the centroid here becomes the center, the mean of the Gaussian. Okay, so after one iteration, you see that the both Gaussians have really changed a lot. So this blue circle here has become a blue ellipse. Now it has started occupying some part of the data set, and this red circle has become the red ellipse, started occupying different part of the data set. And now there's a lot of overlap between these two Gaussians, which is wasteful because you want to capture the two different clusters which are there in the data set. So, but after one more iteration, you see that the two ellipses are diverging, moving away from each other, and each ellipse represents a Gaussian. So, like I said, section of a Gaussian in general is an ellipse in multi-dimensions. So they move further, and after some iterations, you see that very nicely this Gaussian has very tightly fit this cluster, and this Gaussian has fit this cluster. So the two Gaussians capture these two clusters. So this is the kind of thing that we're talking about. It is called expectation maximization. We'll see all that, why it is called like that, we'll see later. Okay, let's not get kind of confused or scared by the terminology. Let's get at the intuitive idea first. Now there is a very interesting data set. The data set we are looking at here comes from this, what is called old faithful geezer. So it's nothing, it's not a faithful geezer or anything, it's just a normal geezer. Geezer is basically it's a what is called a hot water geyser. So in this, I don't have a video here, but if you search the net, you'll find this is located in Yellowstone National Park in US. So the specialty of this is this huge jet of hot water, right, bursts out of this hole once in every so many minutes. It happens with a very high regularity. It's not perfectly periodic, but it happens with a very high regularity, almost like a biological process. And it's obviously a geothermal process, but almost like a biological process. The way the heart beats. Even that is not a very periodic process, but it's roughly periodic. So like that, this water keeps gushing out of this hole once in every so many minutes. And once it gushes out, it stays on for some time before it becomes quiet again. Okay, so the two variables which define the activity of this geyser. One is the on time, that is, once the water starts gushing out, how long will it stay? Okay, and then once it becomes quiet again, how long will it remain quiet? So the first one, which is the on time of the jet, that is called duration. The second is off time, which is the delay. So if you collect these points and plot them on an XY axis, you get two clusters, which is very interesting. So there is some kind of a patterning in the way in which this geyser works. So people have used it as this is a standard data set. It's a very simple data set, just two clusters. So what is happening is in clustering literature, there are certain standard data sets which are like workhorses. So whenever somebody comes up with a new algorithm, they'll try their algorithm on this data set and publish results. So you can compare your output with previously published results. So this is one such fancy data set, very simple data set. So you see that in this case also, if we apply two Gaussian, it nicely can cluster the two clusters present in the data set. Okay, so that's all. Now the question is, how do you do this? Mathematically, how do you do this? What is underlying equations and all that? What are the update rules? All that we'll see in the next class. So brace yourself a little bit of math. In fact, this topic is the only one which is slightly mathematical. All the rest are somewhat straightforward. But anyway, I'll go a bit slow and focusing on the intuitive idea first before just getting into the symbols and equations. Right. So